our last tape, we discussed the construction and operation of substation transformers. These transformers step down the voltage from subtransmission level to the primary feeder level. Now, as you know, one more voltage transformation is yet needed to step the primary feeder voltage down to the customer's service voltage. This is accomplished by the distribution transformer, usually located nearby the customer's premises. A large utility company may have hundreds of thousands of distribution transformers located throughout its service area. So it is important for the distribution operator to know something about them. In this tape, we will take a look at the various types of distribution transformers. In particular, their construction, application, and significant operating characteristics. The type of distribution transformer which we are most accustomed to seeing is the one located on top of a pole, as shown here. But obviously, this type cannot be used for every installation because many customers are served by underground distribution systems. It is not feasible to have just one type of distribution transformer that is equally suited to both underground and overhead service. So manufacturers supply distribution transformers in several basic types depending on the application. For example, we have the pole-type transformer for overhead service, pad-mounted transformers for underground service. These are actually located above ground. Underground transformers, these include the submersible type and also transformers which can be buried directly in the earth. And network transformers, serving secondary network systems and spot networks. And these are usually located in vaults underground. And within these four basic types, there may be many different variations on the design. So let's begin by examining the most common design for a distribution transformer, the single-phase pole-type design for overhead residential service. As we shall see later on, this type of transformer is extremely flexible in application. One outstanding feature is the variety of ways in which internal connections or external connections can be made. Single-phase pole-type transformers are built in standard sizes of from 5 kVA up to 500 kVA and are used on primary systems of 4160 volts up to 34,500 volts. For example, we see here a 25 kVA single-phase transformer applied to a 13.8 kV Y-connected system. The voltage across the primary winding is the line-to-neutral voltage, that is about 8 kV, and the secondary output voltage is 240 volts. The transformer tank is ruggedly designed to protect the core and coils from the elements. The tank top is sealed on tightly to prevent moisture from entering the transformer and contaminating the oil, which is needed for insulation and cooling. The volume of oil contained in the tank is quite small in comparison to the substation transformer. Hence, there is no need to install conservators or other systems that allow the oil to expand or contract and the tank to breathe. Most distribution transformer cores are of the shell-type design, as shown here. The core consists of two laminated steel subassemblies with the high and low voltage windings slipped over the center leg before the core laminations are butted and joined. The coils are arranged concentrically about the core, with the low voltage winding set inside the high voltage winding. The windings themselves are insulated from each other and from the core by impregnated paper insulation. The entire core and coil assembly is usually immersed in oil inside the transformer tank. Now, the cooling method used on distribution transformers is the oil-to-air or self-cooling method. This is in contrast to substation transformers, which often used forced air or forced oil and air cooling. On large kVA-rated distribution transformers, say 100 kVA and above, radiators are often installed on the tank to improve the heat transfer capability. Instead of the radiators shown here, cooling fins may be attached to increase the area of the tank. As with substation transformers, not all distribution transformers are oil-filled. In some applications, dry-type units are used. These transformers are housed in a metal enclosure and cooled by natural circulation of air. Even though the coils are widely spaced, these units still run quite hot. Conventional pole-type transformers do not normally have any protective equipment built in. Instead, it is up to the utility to provide external surge arresters and fusing for protection. By contrast, there are a variety of transformer designs that do include some or all of the necessary protective equipment. For example, in the completely self-protected design, as its name suggests, all protective devices are already mounted on the transformer. In this particular example, we can see the surge arrestor, which is connected between the high voltage winding and ground. The arrestor, as you know, protects the transformer against excessive voltage surges. This internal fuse, which is placed in series with the high voltage winding, it is designed to open in the event of an internal transformer fault. And this circuit breaker, which is located in the low voltage winding. This breaker is intended to protect the transformer from excessive overload or faults occurring out on the secondary circuits. The low voltage circuit breaker uses a thermally sensitive bimetallic strip to sense temperature increases resulting from overloads. Now, overload conditions may be due to either excessive secondary load current, that is, excessive consumer demand, or they may be a result of a fault on the secondary circuit external to the transformer. Some self-protected transformers have a signal lamp that is automatically turned on when the transformer loading exceeds a certain preset value. One type of design includes a relay which indicates the number of times that overload has occurred since last reset to zero. Troubleshooting crews identify such transformers during periodic checks, and this information can help indicate locations where a larger transformer may be needed. Whether the transformer is conventional or comes with protection included, it is important that the transformer fuse and the primary lateral fuse be well coordinated with each other. Why is this? Well, clearly, if a fault occurs in the distribution transformer, we want the transformer fuse to open before this fuse, which protects the system from lateral faults. If the primary lateral fuse blows first, this would cause an unnecessary loss of service to all customers served by the lateral. Similarly, if the transformer is connected directly to the feeder, the transformer fuse and the feeder breaker protection must be coordinated. We will be talking much more about this matter of fuse coordination in a future tape. Okay, so much for the protective devices associated with distribution transformers. Now, let's look at how these single-phase transformers can be connected to Y and delta primary systems. If the primary system is solidly grounded, for example, in a 4-wire Y connection, then the tank of the transformer can act as the grounded neutral. In this case, we need only one high-voltage bushing on the transformer, connecting one of the terminals to one phase of the primary feeder. The other high-voltage winding terminal is connected to the tank, which is in turn grounded externally. A ground connection should be made to the spade lug located on the tank. But what can we do if the primary system is delta connected, ungrounded? Well, in this case, we must have a 2-bushing transformer. Both bushings are used to connect the winding terminals to 2 separate phases of the primary feeder. A 2-bushing transformer can also be used on a grounded Y system. Here, the second bushing is used as the grounded neutral connection. Okay, up to now we've been looking at the most common pole-type transformer design, that is, the single-phase design. However, pole-type transformers are also manufactured as complete 3-phase units, as we can see here. These transformers usually consist of 3 separate coil assemblies, each with a primary and secondary winding, all on a common core, and enclosed in the same tank. For overhead applications, 3-phase transformer banks are usually made up of 3 single-phase transformers connected together. This allows the separate transformers to be equally spaced on the pole, thus distributing the total weight of the 3-phase bank. Typically, 3-phase transformer banks have total ratings in the range of 15 kVA to 500 kVA. Okay, now at this point let's take a break. Then we shall come back and discuss some other aspects of distribution transformers. For now, switch off the tape and review this material in your workbook. Welcome back. Up to this point, we have discussed several aspects of construction and application for pole-type transformers used on overhead systems. Let's look now at distribution transformers for use with underground systems. One particular type of underground transformer is the submersible or subsurface type. These units are designed to operate in an underground enclosure with a top grate to allow the transformer to be ventilated. These transformers are normally used to serve underground residential or commercial loads. The commercial subsurface transformer is usually 3-phase and manufactured in sizes up to 500 kVA. The residential subsurface transformer is usually single-phase and comes in sizes up to 167 kVA, that is 1/3 the size of the largest commercial unit. For underground residential distribution, the pad-mounted transformer is generally more popular than the subsurface type. We see here a pad-mounted transformer in a residential development. The primary feeder and secondary circuits run underground, but the transformer is mounted at surface level, so improving accessibility. The external cabinet is relatively unobtrusive, and simple landscaping is often added to improve the appearance. Pad-mounted transformers are manufactured in both single-phase and 3-phase designs, and are applied to primary systems up to 34.5 kV. The single-phase units are built in sizes ranging from 15 to 167 kVA, while the three-phase transformers can be as large as 2,500 kVA. With pad-mounted transformers, connections are made within the cabinet to the primary and secondary leads and also to the protective devices. In one particular type, the primary bushing terminals are not insulated so that the high voltage leads can be directly accessed from the front panel. This is called a live front design. In an alternative design, to ensure the safety of utility crews, a dead front arrangement is available. Here, all the high voltage equipment external to the transformer, such as incoming primary cables, must be plugged in through separable insulated connectors, or elbows. With this arrangement, no direct contact with the supply voltage is possible from the front panel. Another type of transformer sometimes installed underground is the network transformer. This is specially designed to feed into a secondary network supplying a high-density downtown load. And this type of transformer is also used to form spot networks at or in commercial buildings. Network transformers are always three-phase units designed for primary voltage within the range of 5 kV up to 34.5 kV. The secondary winding is connected in Y with the neutral grounded. Network transformers are typically designed for a secondary voltage of 216 volts line to line, that is 125 volts between one phase and the neutral. Newer, large, high-rise buildings may be equipped with network transformers whose secondary voltage is 480 volts line to line for the supply of three-phase equipment. This gives us 277 volts line to neutral to serve the heavier single-phase loads, such as area fluorescent lighting. And obviously, 120 volts is needed to supply smaller single-phase loads, such as desk lamps, typewriters, and so on. This is provided by another transformer, stepping voltage down from 480 volts to 120 volts. Common kVA ratings for network transformers range from 300 kVA up to 2,500 kVA. These transformers have to be built to withstand the rugged, corrosive conditions that are often encountered underground. When installed above ground, this equipment is all mounted within a sealed, waterproof enclosure. A high-voltage disconnect switch is provided inside an enclosure bolted to the transformer. When it is necessary to isolate the transformer, for example, to perform maintenance, the switch can be opened manually. A viewing window is provided so that one can see whether the disconnecting switch is in the open position. This is often necessary to comply with safety requirements. On the secondary side, a network protector is provided consisting of an air circuit breaker and associated protection equipment. This breaker will open automatically for feeder or internal transformer faults. Remember, the secondary circuits of a network are interconnected to several other transformer secondaries. So power could flow back from the network to a fault in the transformer, for example. To prevent this occurrence, the network protector is equipped with a reverse power relay which senses the reversed flow and automatically trips the protector. The network transformer contains oil for insulation. Cooling takes place by natural circulation through radiators which are installed on the side of the transformer. Usually on the network transformer, high voltage tap changing equipment is provided, but operation must be performed off load. Well, so far in this tape, we have discussed both overhead and underground distribution transformers. But no matter what type of transformer is used, utility planners must determine the optimum size transformer to meet the different needs of the consumers. How is this done? Well, at first glance, one might think that we just add up all of the kilowatt demand of all of the appliances in all of the houses and then install a transformer of that total capacity. However, transformers are never sized this way, since we would wind up wasting a lot of capacity. The transformers would be working at something less than 50% capacity for most of the time. In sizing a transformer, a utility can take advantage of the fact that the customers do not use all of their appliances at the same time. Moreover, the several customers being supplied quite frequently work on a different daily routine, so they tend to balance out each other's demand. This variation in usage of electricity is known as diversity. As a simplified example, let's suppose that one transformer is to supply 6 homes, each with a maximum electrical demand of, say, 5 kilowatts. Now, without considering diversity, we would have a total demand of 30 kilowatts. In practice, the maximum demand would be multiplied by a factor called the coincidence factor, which reflects the fact that not all appliances would be used at the same time. Let us assume in our example that the coincidence factor is 0.75. Then we find that our installed transformer capacity should be equal to 0.75 times 30 kilowatts, that is 22.5 kilowatts. In practice, the utility company would install the nearest standard size, 25 kVA in this case. The actual value of coincidence factor will be set by the utility company based on experience with different types of loads in different locations. The utility company must be prepared for the load to grow and will normally take account of this probability in their installation. For example, in a new residential subdivision, a small 25 kVA single-phase transformer may initially be sufficient. Then, as the subdivision grows, a larger transformer can be installed or additional transformers added. Okay, before we stop for the break, let us briefly review what has been covered so far in this tape on distribution transformers. We discussed 4 basic types used for both overhead and underground applications. These are, number 1, the pole-type transformer, number 2, the pad-mounted transformer, number 3, the subsurface transformer, and number 4, the network transformer. We also briefly discussed how transformers are sized to account for load diversity. Even though all 4 types of distribution transformers differ widely in appearance and application, their basic components are essentially the same. The differences arise from the widely varying requirements of overhead and underground distribution. In the next segment of tape, Ted will be back to concentrate on how single-phase and three-phase transformers are connected to supply a variety of load types. For now, turn off the tape and review this segment in your workbook.
Hello. As you already know, the type of load served by the distribution system can vary from small household loads that are single-phase up to large three-phase commercial and industrial loads. Distribution transformers must be flexible enough to accommodate these diverse loads, especially when making provision for load growth over several years. Consequently, distribution transformers are designed so that they can be connected in many different single-phase and three-phase configurations. In this segment, we will look at the most commonly used connections and see how they serve a variety of loads. Okay, so let's first look at some typical single-phase connections. Now, in order to provide flexibility, the secondary winding is usually split into two separate windings that may be connected in series or parallel. Interconnections can be either internal or external. Now, the most common requirement for single-phase residential service is 120, 240 volt service. Such service is provided by the transformer connection shown here. Typically, the primary voltage, 7,200 volts in this particular example, is taken from one phase to neutral of the three-phase four-wire primary feeder. On a delta-connected primary system, the transformer would of course be connected line to line. The two secondary windings are connected in series with a center tap to provide the 120 volt service. This center lead is normally grounded. With this connection, the customer can obtain 120 volts between the grounded center tap and either one of the two outer secondary leads. He can also obtain 240 volts between the two outer secondary leads for operation of heavy appliances such as the household stove. If 240 volt only is required by the customer, then the center tap can be eliminated and only the two outer leads will be connected to the customer's installation. By contrast, in some situations, only the 120 volt service is required. So we can now simply connect the two secondary windings in parallel, like this, and bring only two leads to the customer service entrance. Okay, so that's single-phase service. Let's now take a look at some of the methods by which three-phase loads are served. The three-phase connections we will be discussing can be made by using either 1. A bank of 3 interconnected standard single-phase transformers, or 2. 1 single unit three-phase transformer. Either way, we can have the phases connected in Y or delta. In the case of single-phase transformers, remember that winding polarity must be kept in mind when making connections. We will further discuss winding polarity in the next segment. Okay, now for serving just a three-phase load, a delta-connected secondary arrangement is normally used. The primary windings can be connected in either delta or Y. When interconnecting single-phase transformers to form a delta-delta connection, as shown here, it is very important that all three transformers be identical. If we interconnect single-phase transformers of unequal reactance or turns ratio, the resulting phase imbalance will cause unequal loading of the transformer, and this can lead to overloading and heating of the transformers, all this in return for no useful work. The Y-delta connection is more common, but this brings us to another possible problem area. Suppose we have the distribution transformer primary winding connected in Y like this, and the transformer neutral is grounded by connection to the neutral wire or perhaps to a separate ground. The primary system here is the typical 4-wire system with a grounded neutral. Now, it is entirely possible that ground faults on other portions of the primary feeder may cause this Y-delta connected transformer bank to trip out. Now, why is this? Well, the line to ground fault will probably cause voltage unbalance, and in this situation the grounded Y connection could act as a conducting path for circulation of fault current. Now, the transformer impedance is relatively low, so the value of fault current circulating through the transformer primary could be quite high, and this would consequently cause the transformer primary fuse to blow. If no fuse protection is provided, it could even cause the transformer to burn out. This is the reason that many utility companies do not ground the primary neutral of Y-connected transformers, nor connect it to the line neutral. Remember, the primary feeder is already grounded at the neutral so as to anchor the primary system voltage. Frequently, as you know, we need to supply single-phase loads as well as three-phase from the same secondary circuit. One way of doing this is actually a variation of the delta-connected secondary that we have just been looking at. As you can see here, it is possible to tap and ground the center point of one phase of the secondary winding. This gives us a 120, 240 volt service from this particular phase. Beware, if the center tap is grounded, you can only do this on one phase. In this connection, all the windings share in carrying both the three-phase and single-phase load, but the division of load is not equal. As with the normal delta secondary, the primary windings are quite independent and may be connected in either delta Y or grounded Y. So, we have been looking at the delta connected secondary, but as an alternative, it is possible to connect the secondary windings in a Y configuration. The neutral point of the Y may be either grounded or ungrounded. Normally, with a connection from one phase wire to neutral, 120 volts can be obtained. Between line to line, 208 volts is available, single phase or three phase. The customer can use 120 volt for, say, lighting, 208 volt single phase for the stove, and 208 volt three phase for his workshop. As a matter of interest, in North America, stoves may be fitted with standard heating elements of either 208 volts or 240 volts. For transformers having Y-connected secondaries, the primary windings may be connected in either delta or grounded Y. It is important to note that where a YY distribution transformer is installed, the primary neutral must be grounded. Why is this? Well, any phase unbalance in the secondary loads will cause the potential of the primary neutral to float if it is not anchored to ground. This in turn could raise the line voltage to a dangerously high level on one or more phases. By contrast, a delta connection allows the out-of-balance current to circulate around the phases. The same problem of floating neutral can occur with single-phase loads which are spread out along the line. The single-phase distribution transformers are connected to different primary phases in an attempt to balance the load. Electrically speaking, it looks like an unbalanced YY transformer connection. Therefore, the primary neutral should be grounded. All of the three-phase connections we have looked at so far are designed for essentially balanced operation. However, we could suffer failure of one phase of the power supply, such as the case, for example, when one single-phase transformer fails out of a three-phase bank. The three-phase load must now be carried by the two remaining transformers. In this situation, an unbalanced transformer connection must be used, such as the open delta. In the open delta configuration shown here, only two single-phase transformers are used, but they can supply three-phase loads. Note that the primary is connected to the three-phase supply, hence the voltage relationships hold. The secondary maintains this relationship between the three outgoing leads. The current for the third phase actually passes through the two remaining windings. The voltage supplied to the load from this open delta is the same as from a closed delta, but the current carrying capability is reduced. Therefore, the power available from the bank is also reduced. The maximum power that can be supplied from such a connection is limited to 86.6% of the nameplate rating of each of the two remaining transformers. This works out to be only about 58% of the original three-phase bank. Utility companies often use this arrangement for new installations where growth of load is expected. Initially, two transformers are installed to serve the load, and then the third one is added as load demand increases. An open Y configuration is also occasionally used with Y delta transformers. Obviously, the delta secondary is needed in order to supply the three-phase load from the open delta. The Y connection on the primary side must be solidly grounded to prevent voltage rises due to secondary unbalances. That we spoke of this earlier. Okay, so that covers the more common single-phase and three-phase distribution transformer connections that are used in practice. Because of the variety of connections available, it is sometimes hard to remember the features of each. For this reason, we have included a listing and appropriate diagrams in your workbook. You can see that the distribution transformer is extremely versatile to be able to supply all the various combinations of single-phase and three-phase loads. In the next segment of this tape on distribution transformers, we shall look at some operating characteristics. But for now, switch off the tape and review this segment in your workbook. Welcome back. Now that we know something about distribution transformer construction and winding connections, let's conclude our discussion by examining some of the operating characteristics of distribution transformers. In particular, we will look at winding polarity, overload and short circuit capability, overvoltage capability, and transformer losses. Let's begin with winding polarity. This subject was briefly discussed in the previous tape on substation transformers. As you remember, polarity refers to the relative direction of primary and secondary voltages. Let us emphasize again that when connecting single-phase transformers to form a three-phase bank, or likewise when paralleling two or more transformers, it is absolutely essential that they be connected with the same polarity. Single-phase transformers are built with either additive or subtractive polarity. What do we mean by this? Well, With additive polarity, the windings are arranged like this. The induced voltage in the secondary is in the opposite direction to the applied primary voltage. As before, the high voltage terminals are typically marked H1 and H2, while the low voltage terminals have X1 and X2 markings. Conversely, subtractive polarity means that the windings are arranged so that the induced secondary voltage is in the same direction as the applied primary voltage. But where does the term additive or subtractive come from? Well, as a test, the lineman can connect the primary and secondary windings in series like this, then energize the primary at some reduced voltage. He can now measure the voltage across these high and low voltage terminals. Now, if the measured voltage is higher than the applied voltage, then we know that the primary and secondary voltages are in the opposite directions. That is, they add to one another. Hence, we call this type of arrangement additive. Conversely, if the directions of primary and secondary voltage are the same, then the secondary voltage will subtract from the primary. Hence, measured voltage will be less than the applied voltage, and we conclude that this is subtractive polarity. Normally, the transformer polarity will be clearly marked on the transformer nameplate. Okay, let us now move on and consider the overload capability of a distribution transformer. As in the case of a substation transformer, overloading of the distribution transformer can cause excessive heating, which will progressively degrade the strength of the insulation. If a distribution transformer is subjected to a large enough overload for a long enough period of time, its life will be shortened. Loading guidelines published by the American National Standards Institute define the allowable magnitude and duration of overloads for distribution transformers. We should point out that these guidelines are quite different than for the substation transformers. Let's look at an example. Suppose we have an oil-immersed overhead distribution transformer operating at a continuous loading of 90% of its kVA rating. Suppose also that the ambient temperature is 20 degrees Celsius and we are willing to accept a 0.5% loss of life in addition to the normal loss of life. According to the chart, we can load this distribution transformer to 270% of its kVA rating for 1 full hour. This represents an overload of 170%. By contrast, on a substation transformer, this magnitude and duration of overload would be quite unacceptable. Obviously, if we overload the transformer for a longer period of time, we must decrease the magnitude of overload to keep within the limit of 0.5% additional loss of life. For a 24-hour period, only a 53% overload would be tolerated. Okay, so much for overloading during normal system operation. But the distribution transformer may also be subjected to very high levels of fault, that is, short-circuit currents. When we have short-circuit current flowing through a transformer, this can be thought of as an extremely high magnitude, short duration overload. This now presents the probability of overheating plus mechanical stresses which could damage or weaken the insulation. Even though distribution transformers have fuses or circuit breakers which should operate to isolate the fault, the transformer still needs to be capable of withstanding these high fault currents, at least for a short period of time. Tables giving short circuit withstand capability for distribution transformers are also published in the American National Standards. In this table, fault current levels are expressed in multiples of full load current. For example, a single phase transformer in the range 5 to 25 kVA can withstand a maximum fault current of 40 times full load current for an extremely short period of time. Single phase transformers whose sizes range from 167 to 500 kVA are capable of withstanding fault currents of 25 times full load current. But exactly how long can this fault current be tolerated? As you would expect, transformers will be able to withstand high magnitude fault currents for very short periods and relatively low magnitude fault currents for somewhat longer periods. For example, this table shows some typical values of short circuit current with permissible times for a single phase transformer between 5 and 25 kVA in size. We see here that this value of 40 times full load current can be tolerated for only about 0.8 of a second. Like substation transformers, excessive current is not the only consideration. Distribution transformers must also be capable of withstanding very high voltage surges. Impulse tests are performed on distribution transformers using a fast rising wave shape to determine the basic impulse insulation level, that is the BIL. For example, an 8 kV transformer connected line to neutral may have a BIL of 95 kV. When the distribution transformer is applied to the system, a surge arrestor will be installed. This will be sized so as to limit any overvoltage at the transformer terminals to a value less than the BIL and with a margin of safety included. Right, let's now move on to our final subject, that of losses on distribution transformers. Given the large numbers of distribution transformers that a utility may have in service, the total energy loss associated with these transformers can add up to millions of kilowatt hours per year. These total losses are made up of two components. One, the no-load losses. Two, load losses. The no-load losses are due to the current that flows when the transformer primary is energized, but with no load on the secondary. This no-load primary current is called exciting current. It is necessary to maintain the induced magnetic flux in the iron core. But it also gives rise to losses in the windings and the core. These no-load losses depend upon the transformer core material and its dimensions. In a typical distribution transformer, the no-load losses will amount to about 1/2 of 1% of the rated kVA. So, for a 25 kVA transformer, this would mean about 125 watts of real power loss, even when the transformer is unloaded. These losses are present all of the time and cannot be reduced without replacing the transformer with a different design. Because no-load losses represent such a significant loss of energy, much research is currently underway to investigate new transformer core materials. The second component of transformer losses occurs when load current is flowing through the transformer windings. These load losses are mostly due to the ohmic resistance of the high and low voltage windings. As you know, load losses are referred to as I²R losses, since they can be calculated by multiplying the winding resistance R by the square of the current, I. So, load losses are proportional to the square of the amount of load current passing through the transformer. Typically, the value of load losses at full load may be as high as 1 to 1.5% of the rated kVA. For a 25 kVA transformer, this amounts to about 300 watts loss. Well, that concludes our discussion of distribution transformers. You must agree that these relatively simple-looking devices can, for some types of loads, end up being quite complex to design and operate. In the next tape, we'll change topics and discuss the various switching and isolating devices that can be found on the distribution system. For now, turn off the tape and thoroughly review this segment on distribution transformers in your workbook.